used to get so jealous of the kid.
Okay, let's start with lecture 15. We're going to talk about jump instruction and loop instructions. Homework 3 is due today. Let's do a quick review on jump and loop instruction, and then we're going to talk about subroutines. We talked about two general types of jump, unconditional and conditional. Unconditional jump, or JMP, takes one operand, that is the target. It always will take the microprocessor to the target address. Conditional jump instruction is in the format of JCC, where CC is going to be replaced with a condition code, and then the operand is the target. It will go to the target address if condition is true. Loop instructions. Loop instructions combine CX decrementation with JNZ test. So using one single instruction, you can perform two operations and make sure the loop will continue or not continue depending on the value in the counter register. You may add additional required conditions using loop Z or loop NZ. The additional conditions you can check. Subroutine is a special program segment that can be called from any point in your main program or in any part of your program. It implements the functions or procedures in high-level languages. For example, in C, you can have any number of functions, and the function name, you can define the operations within that function. In your main program or in any other functions, you can call a function A by just using its name, supplied with necessary arguments. The figure on the left shows you an example where we have a subroutine A. As you can see, we just draw the subroutine A separately on the side, but you need to understand that this subroutine A is just a sequence of instructions. So this subroutine may be in the same segment as in the main program, although they are drawn here separately. From the main program, you can let the microprocessor go to the subroutine to execute the instructions in the subroutine. The way you do that is by using an instruction called call. You're going to supply it with the symbol or the entry point of the subroutine A. Once this call instruction is executed, the microprocessor will continue its execution from the first instruction of the subroutine. It will finish all the instructions in the subroutine until the very end one, which is typically a return instruction. And that return instruction will make sure that microprocessor goes back to its main program right after it made the call. And this can happen another time. For example, here you can see in the main program I did another call subroutine A, and that will take the microprocessor to the instructions in this subroutine, and at the end the subroutine will return and the microprocessor will continue its execution from the next instruction right after it made the call. You may wonder, this sounds like a jump instruction. So what we can do, at least for the first case, is we can replace this call instruction with a jump instruction. I can say jump subroutine A. So that will also take the microprocessor to the first instruction of the subroutine. You are right. Also, in the subroutine, we can replace the very last instruction with another jump instruction. So we can put a label here, let's say B. I can do jump B. So that instruction will take the microprocessor back to the main program.
Always you have to write.
So why do we need to have this call and return? Let's see, if we have this kind of jump instructions here, also here. Let's see what will happen when we make that jump second time. So when we replace this call subroutine A with the jump A, so we will have the microprocessor continue its execution from the first instruction of this subroutine. But once it gets to here, remember we had jump B. And where is B? B is here. So that jump instruction will take the microprocessor back to this instruction rather than the one after our second call. So that's the problem of using a jump instruction where you only have one possible target.
So after the subroutine instruction, always have the return code, right?
Yeah, so the question is, well, the comment is, if we use call and this return, every time after the subroutine is finished, it will have this return as its last instruction, and this last instruction will take the microprocessor back to where it made the call. So if you make the call here, then it will return to this next instruction. If you made the call here, then it will return to this instruction. And of course, we'll see how we make that happen, or how do the call and return instructions make that happen. So subroutine, again, implements high-level language functions and procedures. It's written to perform operations that must be repeated in a program. So if you have a sequence of operations that will be repeated for a number of times, it's better to have a subroutine rather than spell out all the instructions at different places. An actual subroutine code is only written once because we use this call and return pair to execute that part of the code as needed.
What would be an example of a subroutine?
Yeah, we'll have example. So we mentioned earlier that when we make the call to subroutine, we will be able to get back to my next instruction once that subroutine is completed. So how we can make that happen? When a subroutine is called, the address of the next instruction is saved. So back to this diagram, when we call the subroutine, the microprocessor will save the address of this instruction to a special place called the stack. And the address of this next instruction will later be used by the return instruction so that the microprocessor will be able to fetch this next instruction once the subroutine is completed. There's some additional things we might need to do, we often do, in fact, when we design a subroutine. States may need to be saved before the call. Parameters can also be passed. What do we mean by the state? By state, we refer to the values of registers. We have a lot of registers, AX, BX, all the data registers, and also we have pointer registers and index registers. But we only have one set of all these registers. Let's say in the main program, there's an instruction that uses or store the result in AX. Okay, so before we make this subroutine call, AX keeps certain value which will be useful in the following operations. Then when we make this subroutine call, we go into the subroutine A. It's possible that subroutine A also use register AX, maybe as a destination operand. In that case, AX will be modified inside the subroutine A. But in the main program, we're actually going to use the value of subroutine A, the initial value of subroutine A, in later instructions. Then, if we do not protect the value of AX, then that original value is going to be lost because its value is overwritten in subroutine A. Because bottom line is we have only one AX. So that's why we need to save them before we make a call, if we do need to protect the original value in the register. Control of program transfer to subroutine. So that's the effect of this call instruction. This will in fact fetch the address of this first instruction of subroutine A.
So what happens if you call instruction and then choose AX? It's always go back to the original value. Always refer to the original value for the first use.
Okay, so the question is, if subroutine A use AX, would it always get original value of AX?
No, subroutine A, it may change the value of AX because they use AX.
Yeah.
But the following instruction, let's say for the next instruction,
Yeah.
not that one, but the other one.
Okay.
If the following instruction use the AX, doesn't use the AX when subroutine, the value was changed, right?
Mhm.
This time.
Mhm.
I always refers to the AX of the original value of the AX, right?
So
Because you can change the AX of the subroutine A.
yeah.
But the following instruction going to use the change the value of the original value.
So the question is, if we use AX in subroutine A, what value it will use? Is it the original value or the modified value? Is that the question?
We actually use the original value.
Yeah.
And then modify, that's the modified value.
In subroutine X?
Yes.
Okay.
But the value is going to be modified only for the subroutine A, right? If I have another subroutine.
When you modify the value of AX in subroutine A, the value of AX is changed. So if you don't do anything special to protect the value, by protect, we really mean that we save a copy of that value somewhere else and later retrieve it. That's how we do the protection. Okay. So depending on the cases, whether or not you want to keep the value of AX or not. So the case I gave you is that in this main program, I have a value in AX that I will need to keep it intact, because later on here I will use the same, I will expect the value of AX is the same as the one I updated here. Yeah. Right. You can still use register AX, but you need to somehow protect its original value by storing that into a different place and later retrieve it. So the call instruction will transfer the program control to subroutine, and after subroutine finishes, return instruction will go back to the saved address. That's when before we make the call, we actually save the address of next instruction to some special place, and that special place is called stack. Call is similar to jump in the sense that it will change the program execution path. And also we have the target. So depending on the distance between the call instruction and the entry point of the subroutine, we'll have proc near and proc far. Proc near refers to kind of an intra-segment call, and proc far refers to inter-segment call. We may need to save and allocate variables at start, and if so, we'll restore at the end of the subroutine. And we'll see how we do that in the next slide. Last instruction returns to saved address. It's always the RET. RET is the mnemonic of that instruction, of the return operation. The pseudo op after return indicates routine end, and often the time we use NP. Let's look at the example. We have a subroutine called square, and we define as an intra-segment subroutine, proc near. And you can see at the end of the subroutine I use the same name, subroutine name, and P. So this proc near and NP, this is a pair you always use to indicate the beginning and ending of a subroutine. These are just pseudo-op, which means that these lines will not generate any code. These are not instructions. They are different from these push, move, or pop instructions. They are called pseudocode. First instruction we have here is push AX. Push AX and later pop AX. These are the instructions that will write data to or read data from a special segment called a stack segment. We mentioned stack segment at the earlier lectures, but we didn't give you a really detailed description of it. And we'll do that in the next couple of slides. But now you know this push and pop instructions are specifically for putting data into the stack and getting data out of the stack. And stack is in memory. It's like a data segment, code segment, it's in memory. You can see here, we didn't give it any memory pointers to say where in memory. We only have one operand, that is the register. Implicitly, there are pointers into the stack segment, and a data operation will happen at that location, and that's called top of stack pointer. We'll look at that in a few slides. After the push instruction, we have move AL, BL. This is to copy the value from BL to AL. And then we do multiply. When we do multiply, we actually multiply the value of BL and AL, which has the same value, that is the value in BL, the original BL. So what we're doing here is to calculate the square of the original value in BL and put the result into AX. You see, this is where we update AX. That means after this IMUL multiplication instruction, the original value of AX is overwritten. After the multiplication, we copy the value of AX to BX. So at this point, BX has the square of the original value in BL. After that, we do pop AX. This is corresponding to the push AX. Push AX, put the original value of AX into stack, and pop AX will get that original value back and restore it in AX. So this is how we save the state. We have a push and a pop. Here we only protect one register. If your subroutine uses other registers, for example CL or CX, DX, you can do the same thing, but you need to pay attention to the order. If you do push AX, then push CX, at the end, you must do pop CX, then pop AX in the reverse order. That's because that's how the stack segment is operated.
When you say push AX and it gets sent to the stack, you just get thrown on top, and that's why you have to do it in that order.
Exactly. Yeah, when you do the push, that word or double word will be put into the top of stack. And when you do pop, it will get word or double word from the top of stack. So you always operate at the top of stack. It's so-called first in, last out. This is the format of call instruction. We'll do call and then proc the name of the subroutine. This call instruction will save the address of next instruction onto stack. Depending on we do near procedure call or far, or intra-segment or inter-segment. If it's intra-segment, that means we will not change the value of CS, the code segment. We only need to change the value of IP in order to get to the entry point of the subroutine. So if it is near, we'll store only IP, the instruction pointer. If it is far or inter-segment, we'll save both CS and IP. This proc, this operand can be a 16 or 32-bit label or immediate or register or memory operand. If it is 16-bit, we'll use that as the new value in instruction pointer. So the microprocessor will fetch that instruction from the address indicated in IP. If it is 32-bit value, that value will replace both CS and IP. When subroutine ends, the last instruction it has to have is the RET. They will use the saved address to restore to IP, or if it is far subroutine, we're going to restore both IP and CS. This is how the subroutine can get back to the next instruction after you make the call. Now let's work on this example. Assume we have 2 in AX, 4 in BX. Show the results of the following sequence. Assume the address of the first 3 instructions are these following respectively. Okay, here's the solution. So in the main program, when we do call sum, the address of the next instruction will be saved. In this case, because it's a near procedure call, so only the IP, the 008, that number will be stored to the stack. And then the control transfer to here. When we say control transfer, we really mean that microprocessor's execution path will jump to here. It will copy the value of AX to DX, and then it will add the value of BX on top of that. So DX will have the value 6. And when this return is executed 008, that value will be restored back to the IP pointer, and then we can get back to this RET.
Isn't the value of AS 2?
Let's see. We have 2 and 4. Yeah, I think, yeah, that's right. So this value should be a 2. Let's talk more about saving the state. We explained earlier why we need to save state before subroutine starts. Because a subroutine may overwrite registers that might be useful to the main program. When we overwrite registers, their original values are lost. Also, the flags bits will be updated in the subroutine. So if we want to return the original flag bits, we also need to protect flags register. We place data on stack using instruction push. We'll store data above current TOS, which stands for top of stack. And it will decrement SP, the stack pointer. Think about stack as a bag of data, bag of numbers. When you do push, you put more data to that bag. And we're going to decrement SP. So if we have a memory map, we have address from high to low. When we push data into it, we will decrement SP. So the SP pointer will actually move from high to low when we push data in it. Yeah, so that it's kind of non-intuitive when we say top. Actually, this top goes down. So if I draw a memory map, so we always have this SS colon SP points to the top of stack. And our stack grows from this high end to the low end. So the numbers here these are the value data in the stack right now. If you push one more, let's say you push AX, which has value 1, 2, 3, 4, then this 1, 2, 3, 4 will be stored here. And this SP pointer will move. How we move that? We're going to decrement SP by 2 because we just push in 2 bytes. AX has 2 bytes. So this is what we call TOS, top of stack. Stack rows towards lower addresses. New SP points to the start of data just stored. Basic push instruction can store a word or double word. Stack can only operate on word or double word basis. You cannot push a byte and at least a word. You can directly store flags register by using push F. You can use push A or push AD to store 16-bit general purpose registers, all of them, or 32-bit general purpose registers.
So the most significant byte is stored at the lower address line?
No. Still, when you do store storing new data in a stack, it still follow little endian. So I was using the example where we do push AX. AX has 1, 2, 3, 4 next decimal. So that's why, I think that's one here. Thanks for the question. We still use little endian when we store the words without words.
So the top of stack is at the low stack.
Top of stack is the lowest address of the stack, yes.
If the list sequence thing, like, well, yeah, word or whatever. If
Yeah.
it's not AX, it would be.
Yeah, that's right. Yeah, because of the little endian, yes. On the opposite, we can restore value or restore state by removing data from top of stack. And the instruction we use is pop. Data will be removed from TOS and SP will be incremented. So we can later have a pop AX. So the value on top of stack is 1, 2, 3, 4 will be retrieved, will be copied into this AX. And then we're gonna increment the SP by 2. So now here, this is the top of stack. This location here is the top of stack. After the pop instruction is completed.
Are those 2 bytes that we just erased, or are they still there? Maybe
They are still
overwritten?
here. We just moved this SP, or we just changed the value of SP. So we moved the top of the stack pointer. The TOS is now a different place, but the value here in the memory location, that stays there. You can use pop F to restore the flags register, and you can use pop A and pop AD to restore all the general purpose registers. Now this point is very important. Pop instructions generally executed in reverse order of corresponding push instructions. Simply because the way we operate the stack, we always operate at the top.
It says generally, with exceptions.
If you want to cause trouble or just purposely swap values of registers, you can do that. There's no way to prevent you writing that kind of instruction. But if you want to just use push and pop pairs to save state and restore state, then these reverse order should be followed. So we have this push AX and pop AX pair used in this square subroutine because we know the subroutine will change the value of AX, which could be useful in the main program. So we want to save it. So we'll add this push AX, pop AX. Push AX will save the value of AX to stack, and once we finish using AX, register will retrieve the value back from the stack. For push all and pop all, this diagram shows what other things will be stored into the stack. We have this 8 registers. We will store, will save when we use push A instruction. And later when we do pop A, these 8 words will be restored back to their corresponding register. Okay, assume we have a stack and assume the value in SP register, the stack pointer, is 2000 hexadecimal. What is the resulting stack state of each of the following sequences? So we have 3 sequences. First one would be push BX, push AX. And then we have push EBX and push EAX. And then the third scenario is we have push A. So these 3 are independent. They're not executed. So push BX and AX, these 2 are executed one after another. But this push EBX, this is a separate case. So I'll give you 1 minute to work on this. Essentially, I want you to tell me what will be the value in SP pointer.
I don't have, we need to look at AX. AX and BX.
No, I'm not asking the actual bytes in stack. I just want you to tell me which one, the value of which register will be at the top of stack and which one is not at the top of stack.
So,
Yep.
so AX is gonna be on top and BX is gonna be below
Okay.
on both cases.
Okay, let's see. For the first scenario, we push BX, then push AX. So we'll push 2 bytes, then another 2 bytes. So SP decrement by 2, then again decrement by 2. So overall, SP is decremented by 4. So the SP or ESP is 1 FFFC. When we do the push, so first is BX, so this BX here. Sorry, BX will be then SP 4. Similarly, push EBX, push EX will do we'll first put BX onto the top of stack and do SP minus 4, and then AX, then SP minus 8. So overall, the original value of SP is decremented by 8, because overall we're pushing it in 8 bytes. And for push A, actually gonna you hand out this. This is on actually previous slide. Where one instruction, push A, will save a number of registers. In this case, 8 words will be pushed into the stack. So So SP is decremented by 16. And DI will be at the top of stack, followed by other registers.